Okay, so we've had the acoustics intro, and now it's time to dig deeper and look at how we can analyze speech sounds. As usual, this video will review last week, preview this week's material, and note the important dates for the week. So, last week we went through the basic properties of waves. I also shared a video demonstrating how to investigate those properties yourself using Praat. Pretty much everything we learned this week can be directly practiced in Praat as well, and I'll have another video walking through that later in the week. You also submitted the first lab assignment last week. It's now marked and you can review my comments and your grades. I'm sorry that it took so much longer than I intended. I'll work on improving that for next time. Excuse me. So this week we look at analyzing sounds. And just so you know, everything from last week and this week can really be applied to any sound, not just speech sounds, and even non-sound types of signal can be analyzed in similar ways. But we're going to focus on the speech-related applications, of course. And in the next 2 weeks, we'll be really digging into how this all applies specifically to different speech sounds. This chapter opens with a discussion of what it means to have a digital representation of sound, like the one that YouTube is using to store the audio track of this video. Part of the point here is to remind you that there's nothing magic about any type of file in a computer. They're all just numbers. But more importantly for us, you need to know how those numbers relate to the sound quality and to what you can get out of your analysis. The key concepts here are sampling rate, the Nyquist criterion, anti-aliasing, and quantizing resolution. And I want to warn you, you may come across the term bit depth as an alternative name for quantizing resolution. I tend to prefer bit depth because it's shorter and it doesn't take as, it's not as complicated to say. Same idea though. So now that we have a sense of how to convert analog signals to digital and back, we move on to identify several different types of signal. We've already seen pure tones. They're also known as simple waves or sine waves. More generally, we can speak of a periodic signal, which in real life is often more complex than a pure tone, but it does share some of the properties. And in the real world, what we really get are quasi-periodic signals. They don't repeat perfectly. So that's three, right? Sine waves, periodic signals, and quasi-periodic signals. After that, we get noise. Now, the term noise refers to a very specific type of acoustic signal, and I encourage you to be very careful in how you use the word noise or noisy when communicating in a phonetic context. The textbook then introduces impulse as the last type of acoustic signal. In week 9, we'll see quasi-periodic signals, noise, and impulses as core components that help us identify different classes of speech sounds. I also want to mention a sixth type of signal, which is important in speech, but it's left out of the textbook because in a sense there's nothing to say about it, and that's silence. But it will play into some of the speech sounds that we come across and that we discuss, so keep that in mind. After the catalog of speech sounds, we get into some methods for analyzing and comparing different complex sounds, that is, different sounds that have, they're more than just sine waves. And the core of these methods is the Fourier Analysis, named after some old-timey person named Joseph Fourier. We see how complex waves can be created by adding together a series of sine waves, of simple waves, and we get a tool which has some amazing, fascinating, awesome math behind it that we don't even touch in this course, a tool to generate a spectrum, and this is the Fourier Transform. The spectrum breaks any wave down and represents it as different levels of energy at different frequencies. So for periodic signals, which are sort of the core, always the first way that Fourier analysis is introduced, we get the concept of harmonics and their relationship to the fundamental frequency of a sound. And because many speech sounds are quasi-periodic, harmonics are going to come into play again and again as we go forward. We go over the idea of a line spectrum to represent the harmonic structure of these sounds too. The discussion of Fourier analysis comes with two important notes at the end. One is that Fourier transforms are fundamentally about analog signals, about continuous representations of waves. So when we're working with digital sound, which is digitized, it's discrete rather than continuous, we use an adapted version, the discrete Fourier Transform, or DFT. And usually we use it in the guise of a fast Fourier Transform algorithm, an FFT algorithm. That's what's happening in our computer when Pratt produces a spectrum for us, for example. The other note is that although the build-up to our picture of Fourier transforms focused on periodic sounds, we can actually perform this same analysis for any signal. Rather than a line spectrum, we get a continuous spectrum, and since speech sounds are at best quasi-periodic, they're not perfectly periodic, all spectra of speech and real-world sounds are going to tend to be continuous spectra rather than line spectra. Okay, so we've set spectra up. Now we get to work reading them. We look at the idea of windowing, and this is something that can dramatically affect the type of information that is and isn't available in the spectrum. And then we get to one of the most awesome tricks of this business, and that is combining a series of windowed spectra sampled over successive points in a sound wave and building a spectrogram. This is a three-dimensional graph. It has sort of vertical dimension, a horizontal dimension, and it has a third dimension that's usually represented in shades of darkness. In my own research, I have used wide and narrow band spectrograms extensively. They're so central to acoustic analysis of speech that Pratt shows a spectrogram by default whenever you want to visually inspect a sound. Okay, and the chapter closes by introducing another method for analyzing frequency components of a signal, and that's the Lpc spectrum. It's derived using linear predictive coding, Lpc, and this is a non-Fourier method, and it's used in a lot of automatic speech processing. Because of its efficiency, it's been widely used in speech synthesis and speech recognition. We're not going to use it much here, but it is the basis of Pratt's automated formant tracker, which we're going to encounter later. Okay, so what's that? 7 minutes. So much for all the new material we're covering. What about this week's key events? Tuesday is our regular tutorial. That's March 2nd here in Alberta. If you're in a very different time zone, you may be meeting us, Wednesday morning. Wednesday is the third graded quiz. That's open sort of about 24 hours, Alberta, midnight to midnight Alberta time. And that covers the previous 2 weeks of material. So it's Airstreams and Phonations from before reading week and basic acoustics from last week. The second transcription assignment is now posted, and that's due next Tuesday. It's going to be marked along the same lines as the first transcription assignment. And let's see, what else? Yeah, so at the tutorial this week, I'll be ready to talk about this week's chapter, about the lab assignment that was just marked, about the third graded quiz that's open on Wednesday, about the transcription, or anything else that's on your minds. Okay, that's it for this video. I hope to see you at Tuesday's tutorial.